The mysteries of the universe are vast and endless, but every once in a while, humanity takes a giant leap forward in understanding the fundamental laws that govern everything around us. CERN, the European Organization for Nuclear Research, has once again made headlines with a discovery that could fundamentally change our perception of the universe. What if I told you that scientists have detected something so unusual that it could indicate the existence of new physics? Perhaps even the key to answering questions we've pondered for centuries. The Large Hadron Collider, or LHC, is the world's most powerful particle accelerator, nestled beneath the Franco-Swiss border near Geneva. This massive machine, which stretches over 27 kilometers in circumference, has been operational for over a decade, and its mission is simple but profound: to unlock the deepest secrets of the subatomic world. From discovering the Higgs boson, often referred to as the God particle, to testing the boundaries of the standard model of particle physics, the LHC has been instrumental in pushing the frontiers of what we know about reality. But what the scientists at CERN have recently uncovered is something that even they didn't fully expect. It all began with an anomaly, an unexpected result that challenged everything they thought they knew about how the universe works. This anomaly was observed in the behavior of a particular type of quark, known as the beauty quark, which is one of the fundamental building blocks of matter. Quarks come in different types, or flavors, and they are the particles that make up protons and neutrons, which in turn form the nuclei of atoms. However, these beauty quarks behaved in a way that defied the predictions of the Standard Model, the theoretical framework that describes the behavior of fundamental particles. The Standard Model has been remarkably successful in explaining a wide range of phenomena, from the interactions of particles to the forces that govern their behavior. However, it has its limitations. It doesn't include gravity, for instance, and it has no explanation for dark matter, the mysterious substance that makes up about 85% of the matter in the universe. So when scientists noticed that the beauty quark was decaying in a way that didn't match the predictions of the Standard Model, they knew they were onto something big. According to the Standard Model, when a beauty quark decays, it should transform into lighter particles known as leptons, specifically either an electron or a muon. The model predicts that these two outcomes should occur with equal probability, a 50-50 chance for each. But what the LHC data showed was something quite different. The beauty quarks were decaying into muons only about 70% as often as they decayed into electrons. This discrepancy might seem small, but in the world of particle physics, it's a potential game changer. Electrons and muons are essentially identical, except for one key difference. The muon is about 200 times heavier than the electron. This difference in mass shouldn't affect the rate at which beauty quarks decay into these particles, at least not according to the Standard Model. So why was there a deviation? Why were beauty quarks favoring electrons over muons? The only explanation could be the involvement of a new unknown particle or force, something that isn't accounted for in the Standard Model. This possibility has set the scientific community abuzz. If a new force or particle is indeed influencing these decays, it could open the door to an entirely new realm of physics. Some researchers are already speculating that this could be the beginning of a major breakthrough, perhaps the discovery of a fifth fundamental force of nature. Currently, the Standard Model describes three fundamental forces: the electromagnetic force, the strong force, and the weak force. Gravity, the fourth fundamental force, is not included in the Standard Model because it operates on a completely different scale. But if a new force is at play, it could help bridge some of the gaps in our understanding, especially when it comes to phenomena like dark matter and the behavior of the universe on the largest scales. The new particle that physicists believe might be responsible for this anomaly has been given the tentative name Z prime. This hypothetical particle would be a force carrier, much like how photons carry the electromagnetic force, and it could interact differently with electrons and muons. If this particle exists, it would be a groundbreaking discovery, providing new insights into the fundamental workings of the universe. But as with any extraordinary claim, extraordinary evidence is required, and the researchers at CERN are cautious. They know that more data is needed before they can confirm the existence of this new particle or force. In the world of particle physics, confirming such a discovery is no easy task. The Large Hadron Collider produces an immense amount of data, about 15 petabytes per year, which is the equivalent of 15 million gigabytes. Sorting through this massive volume of information requires sophisticated algorithms and the combined efforts of thousands of scientists from around the world. Yet even with all this technology and brainpower, unexpected results like this are rare. That's why this particular anomaly has captured the attention of physicists everywhere. If confirmed, this discovery could have profound implications for our understanding of the universe. It might help solve some of the biggest mysteries in physics, such as the nature of dark matter, the elusive substance that makes up the vast majority of the universe's mass, but has never been directly detected. It could also shed light on the role of the Higgs boson, the particle that gives other particles their mass, and how it fits into the larger picture of the cosmos. Some scientists are even daring to speculate that this new force could help achieve one of the ultimate goals of physics, the unification of all the fundamental forces into a single coherent theory. Unifying the forces of nature has been a dream of physicists for over a century. The idea is to find a way to describe all the known forces, gravity, electromagnetism, the strong force, and the weak force, within a single framework. The Standard Model has been incredibly successful in explaining 3 of these forces, but gravity remains the odd one out. A new force, if it exists, could be the missing piece of the puzzle, bringing us closer to a theory of everything. But before we get too far ahead of ourselves, it's important to remember that this is still an early discovery. The researchers at CERN are continuing to analyze the data, running more experiments to see if the anomaly persists. If it does, and if other experiments around the world find similar results, then we could be on the verge of a revolution in physics. But even if the anomaly turns out to be a statistical fluke, the pursuit of these questions is what drives science forward. It's about pushing the boundaries of knowledge, challenging our assumptions, and seeking answers to the most fundamental questions about the nature of reality. This discovery is just one of many exciting developments coming out of the LHC. The Collider has already made history with its discovery of the Higgs boson in 2012, a particle that was theorized for decades but remained elusive until the LHC provided the necessary conditions to detect it. The Higgs boson was the final missing piece of the Standard Model, and its discovery was a monumental achievement in physics. But as significant as that was, it also raised new questions that physicists are still grappling with today. One of the biggest mysteries surrounding the Higgs boson is why it has the mass that it does. The mass of the Higgs boson is much lighter than what many theories predicted, and this discrepancy has led some physicists to believe that there might be other Higgs-like particles waiting to be discovered. These hypothetical particles could help explain some of the unsolved problems in physics, such as the nature of dark matter or the origins of the universe. The LHC's upcoming upgrades, which will allow it to conduct even more powerful collisions, could provide the answers. By 2029, the Large Hadron Collider will undergo a high luminosity upgrade, which will significantly increase the number of collisions it can produce. This will give scientists more opportunities to observe rare phenomena and potentially discover new particles. The hope is that this new data will help physicists test theories that go beyond the Standard Model and maybe even point the way to a unified theory of physics. The upgrade could also help scientists produce and study more Higgs bosons, which will be crucial for understanding how the Higgs field, the field associated with the Higgs boson, shapes the universe. The Higgs field is a critical component of our understanding of the universe. It's what gives particles their mass, and without it, the universe as we know it wouldn't exist. Stars, planets, and even life itself would be impossible without the Higgs field. But there's still much we don't know about how this field works, particularly in the early moments of the universe after the Big Bang. By studying the Higgs boson and its interactions, scientists hope to gain deeper insights into the nature of the vacuum of space, the stability of the universe, and the forces that govern everything from the smallest particles to the largest galaxies. One of the more intriguing possibilities is that there could be multiple types of Higgs bosons. The Standard Model predicts just one, but some theories that go beyond the Standard Model suggest that there could be several different types of Higgs bosons, each with its own properties. These additional Higgs bosons could help explain phenomena that the Standard Model can't, such as why the Higgs boson's mass is so light or why dark matter exists. Detecting these other Higgs bosons would be a major breakthrough, and the upgraded LHC could be the key to finding them. But what does all this mean for our understanding of the universe? Could these discoveries help us answer the age-old questions about the origins of the cosmos, the nature of reality, and even the possibility of life beyond Earth? Some scientists believe that the answers lie in the realm of quantum gravity, a theory that seeks to reconcile quantum mechanics, the science of the very small, with general relativity, the science of the very large. Quantum gravity could provide a unified description of all the fundamental forces of nature, including gravity, and explain the behavior of the universe at the most fundamental level. One of the most promising approaches to quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. According to string theory, these strings can vibrate in different ways, giving rise to the different particles and forces we observe. String theory also predicts the existence of extra dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions could be the key to understanding why gravity is so much weaker than the other fundamental forces, and they might even provide a pathway to unifying all the forces of nature. However, string theory is still a highly speculative area of research, and it remains to be seen whether it can make predictions that can be tested by experiments like those at the LHC. Nonetheless, the search for a theory of quantum gravity continues, and the LHC could play a crucial role in this quest. By studying the behavior of particles at extremely high energies, scientists hope to gain insights into the nature of space, time, and gravity, and perhaps even uncover evidence for the existence of extra dimensions. The discovery of new physics could also have profound implications for our understanding of the origin and fate of the universe. One of the biggest mysteries in cosmology is why the universe is expanding at an accelerating rate. This acceleration is believed to be driven by a mysterious force called dark energy, which makes up about 70% of the universe. Dark energy is still poorly understood, but it's thought to be related to the vacuum of space and the energy associated with it. Some theories suggest that dark energy could be a manifestation of quantum gravity or even a new type of force that we have yet to discover. If the LHC or other experiments can shed light on the nature of dark energy, it could revolutionize our understanding of the cosmos and the ultimate fate of the universe. Will the universe continue to expand forever, eventually becoming a cold, empty void? Or will it collapse back in on itself in a big crunch? Or perhaps there's a third option, where the universe reaches a steady state and stops expanding altogether. These are some of the biggest questions in science, and the answers could have profound implications for our understanding of reality. As we continue to explore the mysteries of the universe, one thing is clear: the discoveries made at the LHC and other cutting-edge experiments are just the beginning. We are living in a golden age of physics, where new technologies and new ideas are allowing us to probe deeper into the nature of reality than ever before. The future of physics is bright, and the possibilities are limitless.